We tend to think of time as an invisible river, a silent, steady current flowing evenly across the entire universe, carrying everything from the Earth to the most distant galaxies along at the exact same pace. But physics does not recognize that river. In the strict discipline of relativity, time is simply a physical ledger. It is the sequence of records left behind by specific physical events. Look at this historical photo of an early atomic clock. It doesn't plug into an abstract dimension to read the time. It physically counts the electromagnetic radiation cycles of an atom. A second is simply a specific number of those physical cycles accumulating in the machine. Because of this, the time you experience right here, right now, is perfectly reliable. It is a mechanical count of ticks happening in your immediate, isolated environment. The challenge arises when we look at the night sky. We are trying to compare our local records to light arriving from billions of light years away, and we cannot physically carry a clock out there to synchronize our observations. To solve this, it is tempting to invent a mathematical workaround, a smooth, universal timeline that maps out the entire history of the cosmos, assuming everywhere ticks along to the same background rhythm. Albert Einstein's theory of relativity strictly forbids that assumption. Relativity dictates that elapsed time depends entirely on the specific path and gravitational environment of the clock doing the measuring. Our local records and an invented global cosmic time are completely different things. If we mistake the perspective of our local clock for a universal master timeline, we risk introducing systemic errors into our observations. We might literally be misreading the expansion of the cosmos. In its early history, our observable universe was an incredibly smooth, uniform soup of hot plasma. But as it cooled over billions of years, gravity began pulling matter together, creating extreme physical segregation across space. The result is the cosmic web, dense, glowing walls and filaments separated by massive, dark voids. This creates a severe spatial bias. Most volume sits in empty voids, but our planet, observatories, and distance-measuring stars exist deep inside the extreme environment of a galaxy wall. We are not observing the universe from a neutral, average location. We are peering out from a highly concentrated, gravitationally bound extreme. Astrophysics is currently grappling with a crisis known as the Hubble tension. When we measure the current expansion rate of the universe using local stars, the number is significantly higher than the rate predicted by models of the early universe. The discrepancy likely stems from a calibration trap. All local distance measuring tools, like exploding supernovae, are anchored inside dense galaxy walls. The clocks defining our baselines belong to that specific environment. Yet when we build mathematical models of cosmic expansion, we typically use a coarse-grained domain average. We calculate a hypothetical timeline that averages out the huge voids and the dense walls into a single, uniform volume. This illustrates tempo contrast. Because gravity dictates how time accumulates, a clock in a dense wall ticks differently than the domain average's hypothetical clock. Measuring the exact same expansion of space with these two different ticking rates yields two distinct slope calculations. The Hubble tension does not require mysterious new particles or forces. It may simply be a failure of our bookkeeping, a result of untracked regional clock rates varying across the cosmic web. If time is strictly a physical ledger of mechanical ticks, we have to ask a difficult question about the very beginning of the universe. What happens when we run out of records? Traditional frameworks often treat the Big Bang as a literal genesis, the absolute creation of existence, space, and time out of nothingness. An operational view of physics suggests a more grounded definition. The Big Bang is simply the earliest, hottest, most compressed state of our local universe, where our mathematical models remain predictive and our physical ledger is readable. Hitting a boundary where our current physics can no longer look backward does not mean we have found the absolute edge of all existence. It just means our specific local ledger has run out of pages. This leads to a different architectural model for the cosmos. Instead of a single universe expanding from nothing, our observable universe might just be one local patch within an eternal, infinitely extending mosaic of patches. Look at this image of the supermassive black hole in the galaxy M87. It proves an extreme gravitational collapse. an environment dense enough to crush physical records, already exists in our universe. Under specific quantum models, that extreme collapse doesn't end in a permanent singularity. Instead, it reaches a threshold and bounces, violently transitioning from a black hole into an explosive white hole. This local bounce generates an intensely hot, expanding plasma wave, a brand new local cosmos. It provides a completely fresh ledger of time for that specific patch, appearing to anyone inside it as a Big Bang, without requiring the entire mosaic to be created from nothing. There is no universal master clock ticking away in the background of existence. There are only local ledgers, driven by extreme environments. To truly understand the cosmos, we simply have to learn how to read the clocks right in front of us.